Hello and welcome. I'm Parth Patel. In this session, we're going to explore the Dynamic 3D API for WebSpatial. With the Dynamic 3D API, you can go beyond static model display and build fully interactive, programmable 3D content using familiar 3D engine-like APIs. You can compose arbitrary scenes from entities, control transforms, swap materials, respond to spatial interactions, and animate, all from within your React app. Our goal is simple: to make building spatial apps feel as natural and as powerful as building a modern React web app. We'll start with the core mental model, look at the foundational building blocks, and step through practical, code-driven examples you can ship today. By the end, you'll have a concrete picture of how to go from a simple static model to a fully dynamic, interactive, three-dimensional experience, all within the comfort of the web ecosystem you already know. If you haven't set up your development environment yet, check out our companion video on getting started with the Tray AI IDE and the PICO emulator before diving in. In most traditional XR stacks, your application owns the entire 3D world, and everything, even buttons and text, lives inside it. WebSpatial flips that around. Your app stays a normal React app, you just embed 3D content into it, like you'd embed an image or a video. On PICO OS 6, this PICO Spatial Engine manages this shared space and renders multiple apps together. Your app doesn't need to worry about any of that. It just provides content inside spatial containers, regions of 3D space managed by the OS. There are two main types. A window is great for GUI. It keeps a consistent size in your view so text and controls are always readable, even if the content mixes 2D and 3D. A volume acts like a real-world object. It has physical size in meters, looks bigger up close and smaller far away. With the right configuration, a volume can also be used for more immersive experiences. All of these can host the same mix of 2D layout and 3D content. Now, inside any spatial container, you embed 3D content using 3D content container elements. These are HTML elements like model and reality that live in your page and participate in the CSS layout, just like an image or canvas. Don't confuse this with spatial containers. Spatial containers are managed by the OS, while content container elements are part of your code. Inside these spatial containers, WebSpatial gives you two categories of components. First, there are 3D content container elements like model and reality. These behave like HTML elements. They participate in the HTML layout system, support CSS properties, and can be composed with other 2D and 3D elements, just like image, video, or canvas. Then, inside a reality element, you work with entities. Entities are not HTML elements. They don't participate in HTML layout and don't support CSS properties. Instead, they are graphic objects in a 3D world view with their own 3D rendering properties, like position, rotation, and scale. A reality component is your 3D canvas. It lives inside your regular layout. Inside reality, a SceneGraph represents a tree of entities. An entity is a simple container for grouping and transforming other objects. A model entity points to a reusable 3D model. An unlit material gives you straightforward color and opacity. Note that model asset and unlit material are declared as direct children of reality outside the SceneGraph. They define shared resources. Entities inside the SceneGraph then reference them by ID. The SDK also supports a range of geometric shape primitives beyond boxes, including sphere entity, cylinder entity, cone entity, and plane entity. If you think in React components and props, you already know how to use these. They're just spatialized components for 3D content. But remember, unlike model and reality, these entities are not HTML elements. They exist in a 3D coordinate space with their own transform properties, not in the CSS layout flow. Define these materials once, then reference them by ID from any box entity or model entity. There are two complementary ways to get 3D content on screen, and the key difference is scene composition. When you want to display a single 3D asset that integrates directly with CSS layout, the model component is ideal. It is based on the W3C standard model element with the same API. When you add the Enable XR flag, it extends the W3C standard with new capabilities. The model is rendered in the space in front of the backplate, much like a tag for 3D files. Note that model content isn't purely static. It can also be transformed dynamically via the Entity Transform API and responds to spatial interaction events. One key difference to understand: in model, the 3D model file scales to fill the container's width or height, keeping its aspect ratio. The model's size is determined by the model element's size in the HTML CSS layout. When you need to compose a complex scene from multiple entities, primitives, and models, all managed programmatically in a 3D coordinate space, you move into the Reality canvas and build a scene graph. Inside Reality, you can program 3D content dynamically using 3D engine-like APIs, and compose arbitrary scenes by combining entities. A model entity has no intrinsic size. It's an origin point. The model file is rendered at that origin using its pre-authored dimensions, and its units match Reality's default units. Our dynamic 3D API is focused on making this path feel just as simple, giving you full control over transforms, materials, interaction, and animation, while composing entities however you like. Once you move into Reality, the entity model starts to shine. You can load a single model asset, like a spaceship, and then create many model entities instances that all reference that shared resource. Remember, each model entity is just an origin point. The model renders at its pre-authored dimensions in meters, with no intrinsic container size. Each entity has its own position, rotation, and scale. You can arrange an entire formation without downloading the model file multiple times. This pattern scales from a small demo to a complex product configurator, all driven by React props and state. Spatial interaction is where spatial content starts to feel alive. WebSpatial exposes a full set of spatial gestures events directly on entities: on-spatial tap, on-spatial drag, on-spatial rotate, and on-spatial magnify. In this example, we attach an on-spatial tap handler to a box. When tapped, it updates a color in state, and the material reacts immediately. The on-spatial tap event includes hit information, for example, a 3D location you can use to log and use for effects. That hit data is reported in a layout-based coordinate system tied to your Reality container, which is different from the coordinate space you use for entity position, rotation, scale in the scene graph. For drag gestures, on-spatial drag provides a vector that tells you how far the gesture has moved since drag start. For rotation, on-spatial rotate provides a quaternion. And for pinch to scale, on-spatial magnify provides a magnification ratio you can use to update an entity's scale. Today, the simplest way to animate entities is to treat transforms as React state and update them inside request animation frame. A spinning cube is just a rotation value measured in radians that increases a little bit every frame. This works perfectly with your existing React mental model. You can use easing libraries or gesture handlers to drive the same state. WebSpatial is built on a 2D wraps 3D philosophy. Your app stays a regular HTML and React layout, and 3D content is embedded as just another element inside that tree. This has a few important consequences for how you structure your UI. For CSS-based layout, you place model and other 3D content container elements inside Flexbox grid just like any other div, so your 2D and 3D content shares the same layout system. For visibility and opacity, properties like display, visibility, content visibility, and opacity still work as expected and can be used to show, hide, or fade 3D content together with the rest of your UI. For spatialization attributes, when you mark elements as spatial with Enable XR, CSS hooks like XR Back and Transform control how that content floats in depth and how it moves as the layout changes. For positioning, for position relative, absolute, or fixed, they continue to apply even after elements are spatialized, so you can align 3D regions with surrounding controls and text. All of this means you don't have to learn a new UI framework to add 3D. You bring 3D into the CSS and React patterns you already know. That's the essence of 2D wraps 3D. 3D becomes a first-class citizen inside your web layout, not a separate world that takes it over. And on PICO OS 6, this philosophy extends to the platform level. The PICO Spatial Engine handles the multi-app unified rendering, so your spatial app coexists naturally alongside other apps in the shared space. Remember, the coordinate system positive y is up, positive x is right, positive z is towards you. Units are in meters for position and radians for rotation. The origin is the center of your canvas. One important note, when you receive data from spatial interactions, the hit location properties, offset x, y, and z, and similarly, translation x, y, and z for drags, use a different coordinate system. Their origin is the top left corner of the reality backplate, and units are in layout points, not meters from the center. If you need to convert interaction data into entity positions, you'll need to account for this difference. The key idea is to stay in the React mindset. Let the PICO Spatial Engine and WebSpatial handle the hard 3D work underneath. We can't wait to see what you build with it. Thank you.